Hello. We are talking about section 13.5, 2 B and C level problems. One is problem 17, the other one's 19. So here's 17. So the first thing is that you'll notice that you're given this figure here that's been graphed. And what you have to do is you have to verify that OQ, so that's this line right here, and PR, that's this guy right here, have the same midpoint. That's going to be significant because if they both have the exact same midpoint, then what that's going to mean is that each diagonal is bisected by the other one. And if the diagonals are bisected, then our quadrilateral is a parallelogram. We had a theorem way back in chapter 3, I think it was. It's on page 172. It's theorem 5.7. I believe that's chapter 5. Anyways, that theorem said if the diagonals of a quadrilateral bisect each other, in other words, if they have exactly the same midpoint, then the quadrilateral is a parallelogram. So what we have to do is we've got to figure out the midpoint for OQ, and then we have to figure out independently the midpoint of PR, and then if the gods are smiling on us, they'll be the same thing. Okay, so remember, the way you find the midpoint is you take the average of the x-coordinates of the endpoints and the average of the y-coordinates of the endpoints. Okay, so here we have x1 plus x2 over 2. So let's look at these endpoints. 9 plus 0 over 2, that's 9 halves. And then here, 9 plus 0 over 2, that's 9 halves. So the midpoint of OQ is 9 halves, 9 halves. There we have it right there. Now we got to find the midpoint of PR. Okay, same deal. Take the x-coordinates, add them together, divide by 2. 2 plus 7 is 9, divided by 2 is 9 halves. 6 plus 3 is 9, divided by 2 is 9 halves. So look at here, kids. These midpoints are one and the same. That means each diagonal bisects the other one, and therefore we have a parallelogram. Okay, that's part B. Part C, we want to continue to verify that we have a parallelogram, so we want to find the slopes of all of our lines here. Okay, the slope of this line, this line, this line, and this line. Okay, the slope of OP, let's look at this first. Rise over run, 6 minus 0 divided by 2, 6 minus 0 divided by 2 minus 0, okay? So that's 6 over 2, that's 3 halves. Now we look at QR, 9 minus 3, that's 6, divided by 9 minus 7, that's 2. So we have 6 over 2, that's 3. So you'll notice here that the slope of OP and the slope of QR are exactly the same. So that means those lines are parallel. That means this line right here parallel to this guy right there. Looking at the other two lines now, PQ and OR. Let's do this one first. Slope rise over run, 3 minus 0. That's 3 divided by 7 minus 0, that's 7. 3 minus 0 over 7 minus 0, that's 3/7. And then the slope of PQ, take a look at here, 9 minus 6 divided by 9 minus 2. 9 minus 6 is 3, 9 minus 2 is 7, so that's 3/7. So the slopes of OR and PQ are the same, thus those lines are parallel. These guys are parallel right here. So we know that way we have a parallelogram. Then another thing we know about parallelograms is that the opposite sides are congruent. So now part D of this problem wants us to do 4 distance formulas, which is a lot. This is a long problem, admittedly, and maybe I'll put this one on the homework quiz, so be expecting that. But let's do the distance formula and see that all of the side lengths are congruent. Okay, so the distance formula, the sum of, well, here, let me start over. The square root of, the sum of, the squares of, the differences of the x and the y coordinates. Okay, so let's look at OP here. 2 minus 0, 2 minus 0 squared plus 6 minus 0 squared. 2 minus 0 squared is 2 squared plus 6 squared. Okay? I'm going to just leave it like that, and I'll show you why in a minute. Okay, and then QR, okay, we have the difference in the x's, 9 minus 7 squared plus 9 minus 3 squared. So 9 minus 7 squared is 2 squared, 9 minus 3 squared is 6 squared. You'll notice here, this is 2 squared plus 6 squared, this one's 2 squared plus 6 squared. I don't even care to go further. I can see that these are going to be the same answer. That's why I got a little lazy and I stopped early, but that's okay in this case. All right, now we need to do the distance formula on OR and PQ. So OR, let's do this one, okay? 7 minus 0 squared plus 3 minus 0 squared. 7 minus 0, 7 squared. 3 minus 0, 3 squared. And again, I'm getting a little lazy here. I'm not going to continue just because you'll see why again. And then PQ, we're going to have 9 minus 2 squared plus 9 minus 6 squared. 9 minus 2 is 7 squared. 9 minus 6 is 3 squared. And so you'll notice that OR and PQ are also the same. And so they are all congruent, both sets of pairs of sides. Okay? So that is 17. Now the next problem we're going to look at is 19. And again, this is a multi-step problem. It's huge. So let's try this. 19, you're given this triangle OAT, O-A-T. Isn't that cute? They give it a little name of a cereal. All right, good. I might be gluten-free, but hey. And they say that M is the midpoint of AT. Now, look, this is the y-axis and the x-axis are perpendicular, and the y-axis is one leg of the right triangle, the x-axis is the other leg. So here's the right angle, and so this is the hypotenuse right here. And we're given this point here, okay? And we are told that M is the midpoint. We got to find the coordinates. Now, because I graphed it carefully, I could just read it. But let's pretend that I didn't graph it carefully and I needed to find the midpoint, okay? So here are my endpoints A and T. So the midpoint of segment AT, it's x bar, y bar. Remember, x is the average of the x bar is the average of the x's, y bar is the average of the y's. x1 plus x2 over 2, comma, y1 plus y2 over 2. Okay, so here we go. The x's. Negative 6 plus 0 is negative 6 divided by 2 is negative 3. So I'm good there. And then for the y's, 8 plus 0 over 2 is 4. So this midpoint been confirmed algebraically what I did graphically there. Okay, the midpoint has coordinates negative 3, 4. Then we got to find three distances. We have to find MT, which is this midpoint of the hypotenuse to the vertex. MA, same deal, midpoint to another vertex, midpoint to the third vertex. Now, if you remember, we had a theorem a long time ago that said the midpoint of the hypotenuse of a right triangle is equidistant from all three vertices. So what I expect to see is that all of my distances of MT, MA, and MO are all the same. So they better be all the same. So this is kind of a way I can check myself. Okay, so let's just run through this distance formula here. Okay, negative 3 minus a negative 6 squared plus 4 minus 0 squared, and I got to square root that whole thing. Negative 3 minus negative 6 is negative 3 plus 6, which is just 3 squared, and 4 minus 0 is 4 squared. We can see that this is a Pythagorean triple, right? 3 squared plus 4 squared equals 5 squared. This square root, if I squared both sides of this equation right here, I'd see that. So if you don't notice that it's a Pythagorean triple, you can do it like this. 9 plus 16 is 25, and the square root of 25 is 5. All right, so there's MT. MA, just to do this long tortuous route here, negative 3 minus 0 squared plus 4 minus 8 squared. All right, we got that formula set up. Negative 3 minus 0 is minus 3. And then we got to square that. 4 minus 8 is negative 4. We got to square that. Negative 3 squared is 9. Negative 4 squared is 16. 9 plus 16, 25. Square root of 25 is 5. All right, MO. Negative 3 minus 0. Got to square that. Then to that we have to add 4 minus 0. Got to square that. And then here we take the square root of negative 3 quantity squared plus 4 quantity squared. So this is 9 plus 16 is 25. Square root of 25 is 5. Okay, all I'm doing is using the distance formula, which I'll write it out for you guys just in case you forgot. Square root of the sum of the squares of the difference of the x and the y coordinates. So there is your distance formula, which is what I used here. All right. So we compared the lengths of MA, MT, and M0. And we know that the midpoint of the hypotenuse of a right triangle is equidistant from all three vertices. So this is all, in some sense, busy work. In another sense, it's an algebraic proof of this theorem. So it's not busy work. Okay. The last thing we need to do, and this is where this gets kind of tricky, find an equation. Find an equation of the circle that circumscribes OAT. Now, take a look here, and I drew this in. Circumscribe, remember, if you remember this, it means that all the vertices lie on the circumference. Okay? Now, since this is a diameter of a circle, this has to be a 90-degree angle, right? We know that a right angle is in just half of a circle, a semicircle. Okay, so here's what this looks like. So I know that this circle has to be centered at this midpoint because these guys are all radiuses. Here's a radius there, here's another radius, here's another radius. All right, and so we know the length of the radius, that's 5. And we also know the midpoint. I mean, not the midpoint, the center of the circle, HK, which is the same as the midpoint, negative 3, 4. So I just have this equation here of a circle. Whoa, I think I was talking where you couldn't see that. Okay, so we know that the radius is 5, like I said, and we know that the center is negative 3, 4. Okay, and so we have this equation here that the radius squared equals x minus h quantity squared plus y minus k quantity squared. That is the equation of a circle. And now it's just plug and chug. Just plug it in. 5 squared, 5 for the radius, equals x minus h. H we said was negative 3, k is 4, x minus h quantity squared plus y minus k, which is 4 quantity squared, that's 5 squared, equals x minus a minus 3, that's x plus 3 quantity squared plus y minus 4 quantity squared. So you can see that this finally is the equation of a circle centered at the midpoint of the hypotenuse of a right triangle that's circumscribed about that right triangle. All right, that's it, folks. We are done.